Okay, so what we're going to do in this one, first of all, I'm going to save, but we're going to plot the display shape. So this is reasonably straightforward. We've obviously got the node displacements, and we had the original node coordinates as well. So this is in a list format, which is the easiest way to get information out from the Python component. So I just want to process that first of all in a way. So I'm going to use this command called partition list. And what I'm going to say is actually I just want to partition it every 3. So obviously there are 3 degrees of freedom. So there are 3 displacement values at every location. In terms of plotting, I only obviously actually need the X and the Y. But in this version of the script, I am going to extract the rotation just to show you how you can check it back according to any calculations you've done for the example. So what I want now is something called list item. So by default, if I put my lists or my set of lists of 3 in here, that item is 0, so it will output all of those. What I can do though, and I'm just going to, this doesn't really matter, but I'm going to turn the wrap off. So here, if I zoom in and add, you can see then that I've got a set of lists, so that would basically be 0, then 1, then 2 in terms of the indices. And then I'm just going to label this in case I need to come back. So group it, and I'm going to call it UX, so the displacements UY and RZ there. And then in terms of calculating the displaced location for each node, what I'm going to do is I am going to just construct a vector again. So vector, this time I want it from X, Y, and Z components. So obviously the Z we don't need, but the X and the Y will just feed in there. I'm going to flatten the data back into a list. So I just want my list of vectors now. Then what I'm going to do is I'm going to bring across the original points. So we had them back here, so I could take them from here, but actually I'm just going to take them from here. And something that I'm going to do just to try and avoid too many lines trailing all over the place, I'm going to alter the wire display here to hidden. But obviously if I click on the component, it will just come back and I can see what I need. So in order to have the displaced coordinates, obviously what I can do is I can just move the original nodes by the vector that I now have. But I want to do something basically just to allow me to magnify the displacement. So sometimes we might want to actually reduce the amount of displacement that we're seeing. Other times, obviously, we might want to increase it. So I'm going to allow this to range between 0.1 and 10. Obviously, you may need to kind of play around with those values depending on the analysis that you're carrying out. And I'm going to label that slider as magnification factor. So there we go. So then I am just going to have a multiply component like so. So what that allows me to do is just each of these movement vectors I can then multiply by the magnification factor. My original nodes are obviously the geometry that I want to move, and that's the motion. So the vectors is the motion that I'm going to move each of them by. Okay, so what that then gives me, and finally we're getting to where it's useful to see this information in Rhino. So these will be the displaced nodes. So I'll just label them that way. And just to make it really super easy for me to show the displaced nodes next to the original nodes, I'm just going to bring down a wire from there, and I will label these as the original nodes. And then the last step that I can do is obviously to create the displaced elements. What I'm going to do is I'm going to do it in quite a generalized way. So I want my list item like so, and I'm going to bring across the original index values. So we're just zooming out, and these were the index values if you remember over here. So I'm going to bring them across like so. I'll bring the other one for the end node. So this is just allowing me to recreate the original logic, basically. So if I want to see the displaced elements, then obviously I need to put in the displaced nodes for each of these, so you can see them just appearing over here. And then finally, if I construct a line from these, so these will now be my displaced elements, and I'll just label that. So displaced elements like so. And again, just to try and make things easy for me, I'm going to bring across the original elements as well. Oh, sorry, getting a bit ahead of myself. So it's obviously the lines that I'm bringing across, but I'm going to call these the original elements like so. So we'll just hunt back for the original elements. So they were actually all the way back here, but I could potentially have taken them from somewhere around here, but I will take them all the way over. So we have them now as the original elements, and I will just group all of these. So middle click and group, and then I'm going to label this as plotting the displaced shape. I am just temporarily going to turn off the bifocals so that we can just sort of see the labeling a little bit more clearly on everything here. So sometimes the zoom is a little bit temperamental, but I think that's okay. That's probably good enough. So I can look at my displaced nodes and my original nodes. You can see here, if I start increasing the magnification factor, obviously the nodes are moving apart. Again, I might just allow this to change, so this time I'll go in here. So I will do 100, and actually I might just make that 1 for this particular scenario. So you can see now obviously the displacement is not that high. It is, you know, a steel bar with a reasonable dimension, and we're only applying Newton to it, so that seems sort of as we would expect. But if I now increase that deflection magnitude, and actually I'll turn on the displaced elements, you can see how the deflected shape is going on. The other thing that I will just show, and again, I'd encourage you to double check this for yourself. So if we look at the end here, so list item, and a very quick way of looking at the end for a list item is we set the index to -1. So what I can do is I can look, obviously, so here I would be looking at UY. So I can take that out. And if I scroll down to the bottom here, then that is the deflection at the end. What I could do, I just needed to flatten that list, so that's the downward deflection in millimeters at the end. But I could also, for example, look at the rotation. So we have the rotation there. Both of them are negative, as we would expect, but I'd encourage you to go back through and check that those are the values that we expect. Something we can do, and maybe we'll just do this for the downward deflection, so just noting that value at the moment. Obviously, if we increase the load, so I'm going to increase the load by 10 times, what we're expecting now, and this calculation should all have happened automatically, yeah, so the deflection increases by 10 times. So everything, you know, sort of as we would expect, and I've shown you a way that you can just dive in to the list of data and basically pick out items as you need from that. So the final video that I'm going to upload in this set, what we'll do is we'll look at constructing the axial force, shear force and bending moment diagrams, and we'll just check them compared to what we were expecting as well.